Welcome everyone to our first session today, which is on topic of causality. Our first talk is going to be virtual. It's titled Establishing Markov Equivalence in Cyclic Directed Graphs, and Tom Claassen will be presenting.
Welcome all, thanks for having me. Greetings from a distinctly chilly Netherlands. Unfortunately, I could not make it to Pittsburgh this year. I've visited, had the pleasure of visiting a few years ago. I would have loved to be there, but unfortunately it wasn't possible this time. But thanks to the miracle of Zoom, at least we can still give a presentation on our paper, Establishing Markov Equivalence in Cyclic Directed Graphs. Next. So just to give you a quick idea, it's early in the morning for you. So we'll start off lightly with a sort of a gentle introduction of what we're trying to do with causal discovery, and in particular with cyclic models. And then we go on to the actual core, the Cyclic Equivalence Theorem, a lot of work by Thomas Richardson in previous years, and then give this ancestral perspective that we try to develop in the paper and some visions beyond that, what you can do with it. Okay, so next, please. So a lot of people know that a great many of the really important research questions that people are looking into today that have a big relevance for society, people in general, have to do with causality, right? So whether it's for nutrition or racial bias or the climate change, etc. Often we try to understand what's going on, and sort of our goal is basically trying to develop some sort of causal interpretation, causal model understanding of what's behind it. Next slide, please. Oh, this is yeah, should have been I think these are the flat slides. That's a bit of a pity, but we'll try to do it anyway. So the basic sort of development of causal discovery, and the setting is typically that we have the ground truth causal model. We assume that the system we're looking at has this type of ground truth causal model at the top left hand, and that what you observe are data that are generated by the system. So we have experiments, we do studies, we collect data, and those are the observations on the top right-hand side. And now, basically, what we try to do is use these data that we've collected to infer something about the underlying causal model. Basically, this is the goal of causal discovery. And so there are many flavors. We focus now on constraint-based causal discovery. And basically what this entails is that we have some sort of graphical criterion, a means of, if we know the causal model on the top left-hand side, we can use this notion of deseparation. It's a graphical criterion to read off certain properties on the graph. And these correspond under certain assumptions to conditional independencies in the data. And so using the causal Markov conditions, these separations imply conditional independencies in the data. And using statistical tests, we can test for these and basically use that to infer something about the model. And for that, we need faithfulness as well to reason the other way around. So those are the key assumptions that are typically there. So next slide, please. So this is nice. We're doing this a lot since the early 90s, but unfortunately, in many cases, in sort of the real world, the really interesting parts don't take this standard causal model where we assume acyclicity, the famous causal DAG assumption. We have things like predator-prey models in cell microbiology. Lots of processes are trying to balance each other. It's in the economy, it's in climate change itself as well. So in most cases, cyclic interactions, feedback interactions are really important. So next slide, please. And so to give this idea of what you look at sort of the focus a bit on the rabbit and the fox to understand a bit of what's going on there in the cyclic model. So suppose that you have this really simple system with just two members of a population. There can be described by these the famous Lotka-Volterra equations, where the change in the population of either a part, let's say here for the rabbit, dx dt, so there will be change in time over time of the population size, is somehow related to the number of sort of new births of the size of the population itself. But then for the prey, so every time a fox catches a rabbit, so the chances of having many foxes, many rabbits makes that larger. So you have like a reduction time component in your equations, and that would sort of describe one part. For the fox, the other way around. If they catch a rabbit, then they can sort of produce more offspring. And so if you look at the solutions of these types of systems, so this is a very simple one, you can see this on the bottom left-hand side to have this periodic solution over time. in sort of a balanced equilibrium. And if you look at sort of the, you can plot this in the graph and then sort of where the cycle is sort of following the time lag. So it's like a flat cycle. So can you now move to the next slide, please? So if you add a bit of damping, because the previous one that sort of is not a static equilibrium, which makes it more difficult, we cannot really handle that as well, but sort of suppose that there's some form of damping, in this case, like educated prey rabbits that sort of escape the first time are better the next time, and so there's an initial component in, then you typically can get something that converges to sort of an equilibrium situation. So you can see this on the right-hand side, the bottom right-hand side. So if you converge to like a static equilibrium, basically there's still lots of interactions going on, but the population size is no longer changed. And so this is really where we're looking forward to now. So next slide, please. Okay, so that's the setting. Now we're looking at the cyclic equivalence theorem. This is sort of work by Thomas Richardson, and here we get to a bit of the a bit more into the theoretical nitty-gritty. So next slide, please. So for the for our settings, we take certain simple systems. In this case, you can consider, for instance, a linear cyclic Gaussian structural causal model depicted on the left-hand side, which is essentially a set of equations that describe how the values of the variables, the x, y, z, w on the left-hand side of those equations, how those are influenced or depend on the settings of the other variables. And so if you take in this case, right, so they're x and y in this case, maybe there's some unobserved noise components. You could think of this like Gaussian noise that's on there. But for z, for instance, you see in these equations that it depends on both w and y with a certain parameter, and then some additional noise as well. And so the same for w, but then the other way around. So that would match, for instance, to the causal graph on the right-hand side, right? So that's sort of the way of graphically depicting these connections. And so it's again good to emphasize that these are not the differential equations. These are the relations that hold in these sort of static observed equilibrium situations. So depending on different contexts, you see different equilibrium situations arise. That's sort of the data that we're looking at for. So now key implication is that for these types of systems, in this case, the linear cyclic Gaussian model, the directed global Markov property still holds. Essentially, it means that variables are independent of their non-descendants given the parents. And so essentially, the main thing is that this standard d-separation that we used in the acyclic case still applies. However, because of the cyclic constraints, there are now a few quirks that really rise. And this is where a lot of the work by Thomas Richardson is really important. And so our goal here is still to discover the Markov equivalence class. We're looking at constraints, independence constraints, which means that we cannot find the full model, but we're trying to look for the full, sort of as much formative as we can. So there's still possibility that certain parts of the model cannot be identified. And this is all captured by this notion of the Markov equivalence class. Next slide, please. So yeah, and I apologize because now everything appears at once, so it's a bit more imposing than maybe intended. But so we need some key cyclic terminology. And this is sort of where it's different from what many people are maybe used to. If you, like me, you've looked at the work of Thomas Richardson over the years. I've tried it many times and sort of got to a certain point, but never really got the intuition, but now sort of was forced to look into it and really try to understand it. And so this is just an overview of the key terms that we need in order to get to this Markov equivalence. So the notion first is of virtually adjacent. So in this example, we have the cyclic graph on the left-hand side, A, B, C, and D. There's the cycle between C and D. And now we say that A and D, so that's the cross top left, bottom right, are virtually adjacent if they're not adjacent, but have a common child C in the cycle with A and or D. So you can sort of check that this is the case. It behaves essentially like an induced edge in the acyclic case. And this is indicated with the dotted lines or dashed lines at the right-hand side. So you see there's an induced virtual edge between A and D and one from B to C. Okay, then the next, it's the notion of an itinerary, and this is sort of the generalization of a path in the graph, but now it can include both real and virtual edges. So for instance, ACB in the left-hand side is an itinerary with one real edge from A to C and then a virtual edge from C to B. So it's sort of like a generalization there. And this notion of an itinerary is uncovered if there are no two nodes in the path that are virtually adjacent. Essentially, think unshielded, but then sort of for all the nodes in the graph. So that's the first step. And then we get to the slightly more complicated version. So the itinerary ACD, in this case, if you look at the graph on the left-hand side, it's a conductor if C is an ancestor of A or D, and otherwise it's known as a non-conductor. And for conductor, you could think of like the extension to a non-collider, and the non-conductor would be a collider in the standard case, the V structures. And a non-conductor ACB in this case, for instance, you can see that it's a non-conductor. It's an itinerary from A to C to B, and it's not a conductor, so it's a non-conductor. It's known as perfect if C is the descendant of a common child of A or B. Otherwise, it is imperfect. And it's these imperfect non-conductors that really start to make a difference. So perfect non-conductors, those are real V structures. Okay, next slide, please. So then the big one, this is really sort of the where I sort of struggled over the years to get some intuition there. And it's called, and we don't need to go into too much detail, just to mention this notion. So we have the concept of mutually exclusive conductors with respect to an uncovered itinerary. So you have two conductors, and sort of these triples, and sort of connected by an uncovered itinerary. And so in the top part on the left-hand side, you see the cyclic graph. If you include the virtual edges, then you would recognize that there are some additional virtual edges, and you can see that from A to D to F to B would be an uncovered itinerary, and then ADF would correspond with a conductor, DFB would correspond to a conductor, and together they form this mutually exclusive conductors with respect to an uncovered itinerary. And these are also really important because they're also unique to cyclic terms. So next slide, please. So this is now the result of having these concepts in there. This is the cyclic equivalence theorem introduced by Thomas Richardson. And it contains 6 rules. It says that 2 directed graphs are deseparation equivalent, if and only if they have the same virtual adjacency, so think skeleton type, the same unshielded conductors and the same perfect non-conductors. So this is either the colliders and non-colliders roughly in there, but then also the same mutually exclusive conductors. And then there are 2 additional rules that if there are 2 triples that are unshielded imperfect non-conductors, then there's sort of an additional relation. So for both rule 5 and 6, essentially what they do is that they are able to enable you to orient certain edges between cycles. So the example is at the bottom, where you have 2 cycles, CD and EF. And so if there's an edge between those, these 2 rules will allow you to orient those as well. So these characterize the Markov equivalence class. And sort of this is the starting point. So next slide, please. So now to represent these equivalence classes, so to understand when things are sort of equivalent, Thomas introduced a very nice compact graphical representation that uniquely identifies the Markov equivalence class. So it's like a graphical representation where each edge between nodes corresponds to either an edge or a virtual edge in the original graph. There are arrowhead and tail marks to indicate invariant non-ancestorship, so either ancestorship or non-ancestorship. If you don't know or can tell, then we still include the circle marks. This is all very familiar from the standard packs, but then there's one added bonus. This is the dashed underline that is needed to identify certain imperfect non-conductors. And in the two little graphs on the bottom left view, they're both Markov equivalent. They both correspond to the same CPAC on the right. And you see the dashed underlines at these V structures to indicate that these are like V structures. They look like V structures, but they behave differently. Okay, next slide, please. So now we get to sort of an ancestral perspective, trying to make some sense. So next slide, please. So if we look at sort of what Thomas also managed to do there, it's the famous cyclic causal discovery algorithm. This was basically based on this cyclic equivalence theorem, using sort of the statistical tests to identify conditional independencies, and use that to efficiently reconstruct a CPAC from data, which essentially basically was causal discovery from data for cyclic directed models. And so there was a similar version based on these separations, not on data, but if you use directly on the graph. So this is now what we're focusing on for this paper, how to establish whether 2 graphs are really cyclically, or so 2 cyclic graphs are actually equivalent. So a key thing to notice, and this is sort of where I really struggled, is that even though these mutually exclusive conductors are really important, they are not recorded explicitly in the CPAC. And so the motivating question was basically, can we simplify the cyclic equivalence theorem somehow. And obviously then the spoiler is yes, otherwise we wouldn't have this talk. So next slide, please. So looking first at the top, so the key idea, and this is based on the famous DAG-MAG-PAG trilogy from acyclic graphs. So we have a directed graph, acyclic graph, then we have this maximal ancestral representation, and then the PAG. In the previous case, we didn't have this intermediate step. So what we want to do is introduce the CMAG as the cyclic equivalent to the MAG to represent ancestral, to give an intermediate ancestral representation, and rephrase the CET in terms of invariant elements in that CMAG. So we define the cyclic maximal ancestral graph, so the same as intuitively it should be correspond to the same as the standard MAG. Is that there's an edge given a graph G, you can sort of construct the CMAG. You put an edge if there's a virtual adjacency or edge in the original graph. You put a till mark to indicate ancestorship on an edge, an arrowhead if it's not an ancestor, and we still need these dashed underlined triples to include for V structures in the CMAG that have a virtual edge in G. So it's really sort of on a graphical level. And so they're indicated on the bottom right-hand side. It's done as we call it a virtual V structure in this case, to indicate that it looks like a V structure, but it's different. So next slide, please. So then it still leaves the mutually exclusive conductors. But for that, we show that in the CMAG, they take the form of what we now call a U structure. And this is something where we only are interested in sort of the first and the last edge in the CMAG, and sort of connected by undirected edges. And we show in the paper that every U structure that's defined in this way in the CMAG matches this pair of mutually exclusive conductors in original graph and vice versa. And so comparing with the virtual V structures, then both can be seen as arcs into a cycle. So they both actually look very similar. If you look at the on the bottom, so that the graph on the left-hand side shows a virtual V structure into a cycle. The one on the right shows a U structure, but they have sort of similar, they both have just these two arcs into a cycle. And so that means that we can actually treat them as the same thing. And that's where we introduce the notion of the virtual collider triple, defined as it's either a V structure or it's part of a U structure. And it turns out that this is actually sufficient. And that greatly simplifies the representation. So next slide, please. So now we get to the cyclic equivalence theorem, but now on CMAGs. And so you can recognize sort of the greatly reduced complexity. We now have just 4 rules that are needed. The CMAGs have to have the same skeleton, the same V structures, the same virtual collider triples, and these last 2 rules in the original CET now take the form of if you have 2 virtual collider triples, then if you have an edge between them, that's also invariant. And this leads to an efficient procedure to establish Markov equivalence. So next slide, please. And next one again. So essentially the procedure that we now come up with, what we can use based on this version of the CET is we start with the directed graph.
Tom, sorry, your time is over. So if you could a bit speed it up, that would be great.
Yeah, so I'll 2 more minutes and then I'm done. So we started a little bit late. So you convert the directed graph G into the CMAG. That's sort of the standard direct procedure. Then we copy the skeleton and V structures in the CMAG into the CPAG, orient the virtual collider triples that are still left, and then orient the remaining edges between cycles via the final CET rule. And that will sort of give you a CPAG, and then you can directly compare CPAGs between different graphs to see if they're identical, yes or no. The nice thing is this doesn't need any D-separation tests, so the computational complexity skills quite benevolent, even though in practice it's actually even a lot faster. So next slide, please. We'll skip this as this part. Just look at the results on the computational complexity. This is sort of an indication of the previous. So next slide. Just skip this one. So this is an example of the green and the blue lines show the new version. The red and the pink line show the original version to establish cyclic equivalence. And you can see that this scales a lot faster. So for 200 nodes, the difference is like a factor of about 1,000. So that's really very nice. In practice, if you try to incorporate this, for instance, into like a score-based search, but that's for a different part. So next slide, final thing, I guess. So conclusions and future work. So it used to be this ancestral perspective turned out to be very beneficial. Got a very quick graphical procedure. More importantly, so there's still a few things that we need to do. This is for next step, so that we need to recover or the maximally informative CPAC. Right now we can compare, but there's still other invariant elements to be found. And we can use it to try to use it to merge the d-separation for linear and discrete system with the so-called sigma separation that plays a role for nonlinear systems into a single approach using this CMAC. And then for us, the most promising part is that having formulated in terms of the virtual collider triples, it actually suggests a very natural extension of the current CET that doesn't allow for confounders to include unobserved confounders, very similar to the acyclic case, and then it would take something in the form of virtual triples with order. And so that's a very promising step. That's what we're working on now, and it seems to work out quite nice. So that's sort of a really important result from the of the application of this paper. So that was my presentation. Thank you. Post to 5:04 later tonight.
Thank you.
Or later this morning, actually.
The discussant is Arno Bhattacharya, and I believe he's also virtual. So we'll go quickly to Arno.
Hello, can you hear me?
Yes.
Okay, great. Yeah, so thank you, Tom, for that excellent presentation, as well as the very readable paper. Yeah, so just to give a bit of background, so I'm not, I haven't worked with cyclic directed graphs before, but I found your paper very inspiring, and it really encourages me to get into the literature. So just kind of a brief overview. I mean, just to recap in the talk. So we've been talking about directed graph models and cyclic directed graphs, which are useful for capturing feedback. And it's so the question here is about checking Markov equivalence between two such directed graph models. And the two main assumptions in the paper are that there are no hidden variables, and this global Markov property is satisfied, meaning that d-separation implies conditional independence. Yeah, so as has been mentioned, Richardson proved the cyclic equivalence theorem many years ago, but it's quite complicated and ill understood. So I think it's one of the very nice contributions of this paper to kind of bring it back into the forefront and to make it more digestible. Yeah, so I was very fascinated by this notion of CMAG, cyclic maximal ancestral graphs. So from my understanding, so it kind of brings the non-local information into local information, so that the checking between CMAGs, so the equivalence theorem between CMAGs only involves looking at local tests involving triples of variables instead of long paths. So the paper, I think Tom didn't talk about it in detail here, but it gives algorithms to compute a CMAG from a directed graph, and then also Markov equivalence class representation, a CPAG from the CMAG. And I also found the performance improvement quite remarkable. So let me just quickly go to some questions I have for you, Tom. So is there a motivating analogy between DAGs with latent variables, which is a setting where MAGs are typically used, and cyclic directed graphs, which kind of can give some intuition behind CMAGs?
Yeah, thank you for your kind words. So it's a good question. So I think this is essentially, this analogy was one of the sort of the motivating ideas for us to look at this issue and trying to frame it in this way. I think there's a strong analogy between the DAGs and sort of the cyclic and with confounders and cyclic directed graphs, in the sense that both are sort of part of sort of the very general class. And I think that's what we should try to aim for as a community, make sure that we can handle both cycles and confounders. And then if we have a single representation for that, then either the DAGs without cycles or cycles without latent variables or with latent variables would all be sort of just different versions of the same graph, similar to the way that, for instance, if you look at the acyclic case, if you have a MAG, right, so the maximal ancestral graph for an acyclic graph, then a DAG is also a MAG, right? So there's a strong connection that's there. I'm not sure if that's what your question
is.
is.
I mean, what I meant is, I mean, when you don't have latent variables in the acyclic case, then yeah, you just have the DAG. I mean, you only need to go to the MAG representation.
In interest of time, I need to actually stop this. I'm sorry, we are over time and I need to keep the rest of the session aligned. So thank you for the excellent presentation and the discussion, but we have to move on to our next talk, please.
Okay. Right, thank you.